All right. Given a sorted array of distinct integer and a target value, return the index if the target is found. If not, return the index where it will be if it were inserted in order. You must write an algorithm with O of log n runtime complexity. So basically, what it's saying is that we are going to be given a sorted array and you'll be given an integer. For example, we have this sorted array, and if we were given an integer 5, right, we have to find where that integer is in our array. So we have to find the index in our array, right? So in this array, we have index 0, 1, 2, 3, and we're given integer 5. 5 is in our array. So we are supposed to return index 2, which is the position where 5 is. And if 5 is not in our array, we are supposed to return the position where it would have been if it was in our array. All right, so let's try to solve this. Remember, we want O of log n, so we can't use the for loop. We're going to use a binary search. So let's walk through example 1. What we're going to first do is that we are going to find left and right. We're going to divide and conquer. If you don't know what a binary search is, let's use like a phone address example. Let's say you have a phone address book that is arranged alphabetically, and you're looking for someone that is named Dixon. You have the choice of opening your phone book page by page, which would be the O of n alternative, but we don't want to do that. You probably just want to open your address book to a random page and just try to find letter D, where letter D is located, right? So if you open to M, you just open and you open to M, you will know that you have to go back to the left, to the front, because D is before M. And if you open to C, you know that you have to go backward because D is after C. Do you get the point? So that's literally what a binary search is. It follows the divide and conquer. So here we'll note our left. This is our left will be 0 because we our index 0, and our right will be our array length minus 1. So the length of the array 4 minus 1, which is index 3. So we have our left and we have our right. And then we find our midpoint. Our midpoint will be left plus right divided by 2. That is 0 plus 3 divided by 2 is 1.5. If we math.floor that, we get 1. So this is our midpoint. Now, this midpoint is what we will take and compare with our target. So here, we have our midpoint to be at index 1, which has value 3. Now, let's compare 3. Is 3 our target? No. Is it greater than our target? No. Is it less than our target? Yes. So that already tells us that our target is not going to be in front here. Our target is not anywhere around this area. Our target will be here around this location. So we take our focus off this location and we concentrate on this location. Just like in your phone book where you are looking for Dixon, you open to C. You concentrate on everything after C. You forget about A and B because you know that your Dixon cannot be there, right? So that means we have to change our midpoint. We have to change our left and change our midpoint. So we will move our left to our midpoint plus 1. So our left, we move to our midpoint plus 1. So our left, we move here. Now we have to look for our new midpoint since we have new concentration area now. So left plus right, that's 2 plus 3, that's 5, divided by 2, that will give us 2.5. So 2.5 with math.floor will be 2. So this will be our new midpoint. In this case, we take this midpoint value, 5, we compare it to our target. 5 equals 5. So we're going to return, if the midpoint is equal to the target, we return that. So we return 2. In this case, our response, our algorithm must return index 2. Now let's change the target here. Let's change the target to 2, right? Now, of course, we are just starting. Our left will be the first element and our right will be the last element. Now we have to look for our midpoint, left plus right divided by 2, 0 plus 3 divided by 2, that's 1.5. If you floor it, that will be 1. So this will be our midpoint. Our midpoint is 3. Now let's compare 3 to 2. 3 to 2, we compare both. They are not equal to each other. 3 is greater than 2. And that tells us that our target is not going to be in this location. Our target will be somewhere around here. So we take our focus off this area. We take our focus off this area, right? So we change our left and right and take our focus off this area. So we shift our right to our current midpoint plus, so we shift our right Instead of earlier when we shifted our left because our target was more, now our target is lower. So we shift our right to our midpoint plus minus midpoint minus 1. So our midpoint, which was here before, we move to this place and it will become our new right. So this will be our left, this will be our right. 0 plus 0 divided by 2. This is also still our midpoint as well. Now let's compare it to our target. 1 is less than our target. Our target is greater than 1. So we move our left because in this case our target is greater than our midpoint. So we move our left to midpoint plus 1, right? I know it's a bit confusing, but let me cook. So our left will come back here. Now in this case, so now that we have this awkward situation where our left is greater than our right, then we return our left. So that means that 2 will be in this position. 2 is not in our array, and that's why we've been going up and down. 2 is not in our array, but if it were to be in our array, it will be in position of index 1. So now let's write the code. So now we create our left and right. We've been using left and right since morning. So let left equals to 0, which is our initial value of our left and right, and let right equals to nums.length minus 1. Now we have a while loop. We create a while loop. While left is less than or equal to right. So as far as our search window is still valid in this case scenario, remember at this point, when we got to this point, our search this thing was no longer valid because our left was now more than our right, but we'll deal with that in the code, right? So let's open up while loop. Let me format this. Let's open up this while loop, and then once we have our left and right, we get our midpoint. Let mid equals mat.floor left plus right divided by 2. That was how we were getting our mid, remember. Now if the number at our midpoint is equal to our target, we return our mid, right? If nums is equal to target, then we return our midpoint. Now else if our target is less than nums mid, the value at our midpoint, if our target is less than it, then we move our right. Remember that was what we did, mid plus 1. We move our right. But if our target is greater than our mid, else we move our left, mid plus 1. Actually this should be mid minus 1. We move our right, and then we move our left. We increase our left to a greater index, but if it is less than, we reduce our right. And at the end of it all, we return our left. So there's already a return statement here. For example, in the first example that we did, where we're looking for 5 and 5 was in our array, this line 12 would have sorted that because it would have found the target and it would have returned it. It would have found it as an element in the array and it would have returned it. But in the case of 2 that we eventually did, there was no way this line was going to run because our target is not even in the array at all. So in that case, line 16 will most likely run. All right, let's see. Let's run our code and see what's up. All right, so all 3 of our test cases were accepted. First test case, we were looking for 5. That was our first example. 5 is already in our array at index 2. So we got an output 2. In case number 2, we were looking for 2. 2 is not in our array, but if it were to be in our array, it would be at index 1. Case 3, we have 7. 7 is not in our array, but if 7 were to be in our array, it would be the last item on the array, right? Because we have 6 and then it should be 7. So our output here will be index 4. All right, let's try to submit this and let's see what we have. Okay, our solution was accepted. Honestly, personally, I think the binary search approach can be a bit confusing, but take it one by one. Look through this video and try to solve it on your own. Try to understand it, right? We are trying to make sure we don't go through each element one by one so that we can achieve the O of log n algorithm, right? If you don't know what all of these complexities are, O of n, and it's confusing, it's jumping over your head, please, I have a video on that. I'm going to just attach that. You can watch that video first and understand big O complexities. But yeah, back to our question. If you don't really understand how this went about, take your time. It's like using a phone address book, right? Or it's like checking through a large database of sorted number. For example, if you have 1 to 20 sorted, for example, if you are looking for 12, we don't want to have to check one by one, one by one, one by one. We just want to get to the midpoint. We just open to the middle, 10. We're looking for 12. 12 is more than 10. So we look to the back. But if to say we're looking for 8, we will look to the front. That's literally just the logic. It is straightforward, but it can be a bit confusing, right? Just take your time. I wish you all the best. If you like this video, you enjoyed it, you learned something, please don't forget to like, don't forget to comment, don't forget to subscribe, don't forget to turn on notification for more tech and coding content. See you in my next video. Bye.